Welcome back everyone to the final session of our MS Study Jams from Team Grey Interface. My name is Nilesh Raj and today I'll be taking this lecture on linear regression and logistic regression. We'll start by revisiting some definitions of machine learning as different types. Then we'll move towards supervised learning. We'll talk about the two main types of supervised learning algorithms, that is regression and classification. Then we'll look at one regression model, that is linear regression, and one model for binary classification, that is logistic regression. So let's start this lecture. First of all, what is machine learning? Machine learning is all about data. It is the art and science of learning patterns from data. Now, when do we say that we learn some task? We learn some task if we get better at it with experience and practice. Similarly, a program or a model is also said to learn a task T if it gets better at it with experience. Now, where will it get the experience? The experience is fed to it in the form of data during the process of training. Now, we need to quantify this process of learning. How will we say that our model has learned or not, or how much it has learned? So, we introduce some performance measure to measure how much it has learned. Now, this quantification varies from situation to situation, from model to model, but the general idea is that we need to quantify it. Now, the traditional approach is that we have some input and we have some predefined rules, and these predefined rules are applied on our input to give us some output. This is in general how our algorithms work and so on. But in machine learning, we give our model input and output pairs, and it tries to learn relationship between those two pairs. That is to say, we do not know the rules what is in there in this black box. The core idea of training is that we are feeding it several examples of input output pairs, and it tries to learn some mapping, some relationship among these pairs to infer these rules by itself. So moving towards the types of machine learning, we have three major types, those being supervised learning, unsupervised learning, and reinforcement learning. In supervised learning, during the process of training, we provide our model with labeled data. Now, what is labeled data? When we're giving both the input and the output to our model. That is to say, suppose let's take a very simple example. We have to compute the square of two numbers. Now, we do not know that we're computing the square. We only have data points as examples. So, for example, your data points is 2, 4, 3, 9, 4, 16, 5, 25, and so on. And it is the model's job to derive some relationship between this input and output so that it can generalize better to new examples. In unsupervised learning, the goal is not to learn a mapping, it is to find patterns within our data. For example, we can give it a lot of data and can partition it into different clusters to tell, yeah, these things look same and these things look similar and so on. For example, when you do online shopping, the algorithm can group together items that you purchase like together, like bread and butter and so on. Reinforcement learning is a different thing. It is about an agent that learns by trial and error. So we have an agent, which is basically anything, any program, any model. It could also be a human, but in this case, we're talking about models. It just does something in the environment, and it receives rewards or penalties depending on whether it did good or whether it did bad. It is kind of like training a dog. Like you're training a dog to catch a disc, suppose. So you throw a disc. If it brings back the disc, you give it some treat. If it does not, you reprimand it. So this is exactly like that. The program learns by hit and trial. This is about reinforcement learning. Now coming to supervised learning, there are mainly two types of tasks that are there in supervised learning. One of them is regression and one of them is classification. Now what is regression and what is classification? So the entire goal of a model is to predict something. So what it predicts, that defines whether it is a regression problem or it is a classification problem. If it is predicting a continuous value, then it is a regression problem. If it is predicting discrete values, then it is a classification problem. Now, what does that mean? Suppose you want to predict what will be the temperature tomorrow. Now, the temperature is a real number, it is a continuous value. So, this is a regression problem. But suppose you want to classify emails as spam or not spam. Now, here there are only two possible buckets that the model can classify our data as. It's either going to be the spam or not spam. So this is an example of binary classification. We can also have multi-class classification. For example, you have a data set of suppose all 10 digits, and the model classifies whether a digit is 5 or 6 or 0 or 1 or whatever digit. Another example of regression could be the prediction of housing prices in your city given the data about it. So let's move to linear regression now. Now, linear regression is first of all a regression model, so it will be used for continuous value prediction. Now, how does it work? So it is linear in nature. What does that mean? If you have input features as x1, x2, x3, xn, as in if these are the our input features, and let's suppose y hat is our output target, this is just going to be some linear combination of these input features. That is the core assumption of linear regression. Now we call this y hat as our hypothesis function. This is basically going to be our predicted output. These x1, x2 up to xn are our input features. Now these weight W0 is the bias and W1, W2 up till W1, these are the weights of our model. Now these weights and biases are what we call as trainable parameters. Now during the process of training, we're going to feed our model several examples of of all of our x values and our true output. So that is the value of x1, x2, xn and y for a lot of different cases, and it will try to learn some relationship between these variables. That is, it will try to estimate the values of these parameters. That is what happens during the process of training. It tries to guess the values of these parameters, and the more data you give it, the more better these assumptions will be. Now let's just take a very simple example with one input variable and one output variable. I'll just call it, this will be just be a straight line equation as y is equal to mx plus c, where m is the slope and c is the intercept. Now this will just be a straight line equation. You just can vary the values of m and c, and this line will change in this plane. So these m and c will be derived in the process of training by feeding it multiple outputs. Suppose we have a few different outputs. Suppose we have 2, 4, 3, 6, 4, 8, 5, 10, and so on. Now, what the model will do, it will first of all, we don't have this line during the process of training. We only have these data points. What are these data points? We have 2, 3, 4, 5, and for these we have outputs as for 2 we have 4, for 3 we have 6, for 4 we have 8, for 5 we have 10. We only have these data points. What the model will try to do, it will start with a random line and will try to make it get it closer and closer to these data points. Now you might be wondering that, okay, fine, these data points could be fitted on a straight line, but not all data points can be fitted on a straight line. So what will happen then? So in that case, what happens? Suppose this is our data set. We have some random points here and there. Now it is very clear that one straight line is not able to cover all of these. What our model tries to find is the line of best fit. Now how will it estimate the line of best fit? We need some loss function, we need some cost function. How does that work? So we want to see this is the true data point, and this is the one predicted by our model. Now this difference, we call it as the error. Now we take this error for each of these points, for each true value and its estimated value. We compute these error. Now we can use and we'll perform the mean squared error of these, and that will be our loss function. So here I have done that. Here, as you can see, this is our hypothesis function y hat. This is our predicted output, which is basically this line. These green points are our actual data points. The mean squared error is just the difference between them squared, and then we are summing them up and dividing by n for the average. Now, one might ask, why do we need to square it? So first of all, one benefit of square is that we convert the negatives to positive, because here it doesn't really matter if the point is above the line or below the line. It just matters that it deviates from it. So another question could be, we can use something like mod. Like mod also does that. Why not use mod? So the thing is, we can also use mod. It is a different metric. It's called the mean absolute error. But this mean squared error is more popular because first of all, mod is not really a nice function. I mean, it's a good function, but a polynomial function is generally preferred because they're differentiable in its domain once or twice or multiple times. However, mod is not really differentiable at uh, one point in its domain. So this mean squared error is preferred. Now what will happen during the process of training? We'll start with some random values of all these trainable parameters. These are initialized randomly, and we'll try to get the value so that this mean squared error is minimized. Now by saying we can just take the derivative and equate it to 0, we'll get the values of this. That works in this case. That is called the normal formed equation for linear regression. That is one possible solution. But as this number of parameters grow, that process gets very expensive. and that doesn't really generalize well to other models. So we'll look at a different thing that is called gradient descent. So what is gradient descent now? Gradient descent is an algorithm that allows us to find the minima of our loss function. Suppose this was our loss function. Initially, we have some random values of our parameters. So suppose we lie here on our this loss function. We want to reach the minima for this particular graph. That will be this case. So what we do, we compute the gradient at this point. What will the gradient gives us? The gradient gives us the direction of steepest ascent. We'll go in a direction opposite to the gradient. So in this case, we'll go in this direction. We'll get to this point. Now here again, we'll get another data point. We'll train it. Now again, we'll compute a gradient. We'll go in the negative direction of the gradient, and so on until we reach our minima or whatever data points, how many data points we have, how many times we're showing it to our model. Now, gradient descent is not guaranteed to give you your minima. Suppose we had something like this. Now, this is now the global minima. But you can see that as soon as we reach this point, if we started off here or somewhere here in this place, if we start, we will reach this minima. We'll never reach the global minimum because it will just get stuck here. So that is one limitation with the brute this version of gradient descent. It completely depends on the initial randomization values of m and the different parameters. If we started off somewhere here, then we could have reached here. Even in that case, that was not guaranteed. Like it is possible that if we are taking this step size, it also depends on this step size and number of data we have. If this step size, suppose we start here and the step size was too small and we only have this many number of data points, we'll have to we'll reach here and will not go any further. Now this is we are stopping before we are converging because of the limited amount of data. So this step size also plays a very vital role. Suppose we started here and we our step size is very high. Like we have very big step size. Suppose we go from here to here, then we jump from here to here, here to here. So in this case, what will happen is just keep jumping around. We won't converge to a minima because of the large step size. Now this step size has a formal term for it. It's called the learning rate. So suppose we have a very simple equation y is equal to w naught plus w1x. Now we initialize w naught and w1 with some random values. Now how do we as in start to update it with each data point? So after one data point has passed, w naught is updated as w naught minus learning rate times the partial derivative of the loss function with respect to w naught. Now this is exactly what we call the gradient with respect to w naught. This is called our learning rate. This is actually a hyperparameter. It's different from these trainable parameters that we had. So these parameters are trained during the process of training. This is a hyperparameter. That means it's not really trained. Its value is fixed at start and it stays constant throughout the training process. Now there are versions where it can vary, but it's not really learned during the process of training. Similarly, W1 can be updated as W1 minus the learning rate times the gradient of loss function with respect to W1. Now, this is what we call as gradient descent. Uh, Now, every model makes some assumption about the underlying data. For linear regression, that assumption is that whatever data we are feeding it is inherently linear in nature. If there are any deviations from it, it is just due to noise in the real data set. For example, here we can see that there is no one line that can fit all of these points. So linear regression assumes that it was fundamentally linear in nature, but because of some noise due to real world data, it has deviated little bit from this line. Now, if we are not willing to make any assumptions about our data set, there is no reason to prefer one model over the other. This is actually a theorem that can be proven in machine learning. It's called the no freelance theorem. It basically states that if you're not willing to make any assumptions about a data set, there is no reason to prefer or say that one model is better than another model for that particular data set. So you need to explore your data set, you need to get to know about it, you need to observe it, you need to observe some patterns, then you can decide what model to train it on. So that is why data pre-processing and exploratory data analysis is very important before actually training any model on it. In practice, what we do is we do that exploration, then we train a few different models based on it. For example, even we can train a few different linear regression models with different values of learning rate, and we can see which performs better. So we'll now look at some evaluation metrics. Evaluation metrics are basically to tell you if you want to compare two different models, like which one is better. Now, these are some evaluation metrics for regression tasks like the mean squared error, mean absolute error, and root mean squared error. We've already seen the mean squared error and the mean absolute error. The root mean squared error is nothing, it's just the mean squared error, but we just take the square root of it. Now, why do we take the square root of this? Because if you remember, in the mean squared error, we squared the differences. So that kind of changed the magnitude in comparison to our data set. So if you take the square root of it last, it normalizes the error kind of, and it brings it back to the, as in the relative magnitude of the data set values. It doesn't really matter if you minimize the root mean squared error or the mean squared error, because since root x is basically a monotonic function, it is something like this. If you want to minimize the value of root x, you just minimize the value of x. So to minimize the value of root mean squared error, we just need to minimize the value of mean squared error. So we can skip the extra computation of doing the square root of the error during the training process. So that saves us some compute. Now, few more things about the training process. So whatever data set you have on which we are training our model, we do not train it on our entire data set because we don't want it to just memorize our data points that we are giving it. Like we want it to generalize better to new points, points which it has never seen. We don't want a fancy lookup table for our model. So what we actually do in practice, we take the majority of our data set and we keep it as our training data set. That is, we'll feed this much to the model in the process of training and we keep the remaining as our testing data set. It can be a 70-30 split, it can be 80-20 split. It can, in some cases, it is even a 90-10 or a 60-40, but it's generally 70-30 or 80-20. You can decide that how much you want to keep aside for your training and how much you want to keep for testing. It is basically a balance between how much data points you have. If you have too little, I guess 70-30 might be less effective. If you have too much data, then it might be better. So during the process of training, the whatever loss function you have taken, suppose you take the mean squared error, that will be actually be your training loss. So during the process of training, you are trying to minimize your training loss. That is different from whatever values it will give for new data that is never seen. That is why we are testing data set. And when you come after you train the model, you can use your testing data set and predict values of these inputs through the model. And you compute that error on the same metric. For example, we compute train our model, we minimize our training loss. Suppose our model is not trained. Now we feed it our testing data and we compare our testing loss, which is not called a testing loss, actually called a generalization loss, which is basically how well your model generalizes to new data point. Uh, Even if we get suppose a training loss of zero, it doesn't really matter if we have a very high generalization loss. That means we are doing something wrong, and that is basically our model is trying to remember our training data too much, and this is a problem that is known as overfitting. So let's talk about overfitting and underfitting now. What is overfitting? It is basically your model is trying too hard to just memorize your training data. It is feeding too much into training data. It has basically become a fancy lookup table for your training data. For example, okay, this is not possible in as an overfitting is possible in regression. I'm just giving a different example. Suppose like this, if you are suppose you're using something as say polynomial regression or something, and your model kind of fits like this. Now you can see that this will give like almost 0% loss on the training data, but it will generalize very poorly to our new data because we can see that this was inherently linear in nature. So a line like this would have been much better than that. So that case was called overfitting. Now let's talk about underfitting. So underfitting is basically that you are not even able to minimize your training loss properly. And that can be several reasons for that. For example, your model is simply not complex enough to capture the distribution of the underlying data. For example, here in this case, this data is inherently quadratic in nature. A linear model will never be able to, as in, fit to it completely as a quadratic model would. Suppose if we force a best fit line, it will look maybe something like this, but it won't really generalize much better to a lot of different points. So that condition is called underfitting. There can be several reasons for overfitting and underfitting. For overfitting, one of the reasons could be that you are showing it the training data too many times, or your model is just you're taking a very complex model for a very low data set and so on. For underfitting, it could be that your model is simply not complex enough to capture it, or even if the model is complex enough to capture it, you are not able to converge to that minimum gradient. That is, you don't have enough data, or you have a lot of bad data. You might have outliers in your data. That is another reason for that. Now let's talk about another idea that is called cross validation. Suppose you're training two linear regression models, but one is using eta 1 as your learning rate and another is using eta 2 as your learning rate. Now, since they are different learning rates, these models might behave differently. How do we say that one model is better than another? Again, we can train both models and just evaluate them on the evaluation metrics like the mean squared error or the root mean squared error. But how do we optimize it for the best value of eta? Like, how do we get the best value of this hyperparameter? It is not learned in the process of training because it is not a trainable parameter, it's a hyperparameter. So one way to find it is through cross validation. Now, what we do in cross validation, uh, suppose we are splitting our data. Let's talk about the case before cross validation. We had our training data, we split it into our training set and our testing set. Suppose 70% was our training set and 30% was our testing set. We train both of these models on our training data, and then we add checking the error on the testing set because we want our generation error to be minimum. So we check both of their errors on the testing data set. And now whatever which one has the less testing error, we call it like, yeah, that's the better model. But now we want to find the best value of the learning rate. Suppose we train 100 different models with 100 different learning rates, and then we check their value on the testing data set, like which provides the least generalization loss, least generation error. Uh, this is also called a training error, or this is also called a generalization error. Uh, so we trained 100 models, and now we are checking which has the least generalization error. Now what happens? We take that value of the learning rate and we like use that model. Now when that model is in production, like when it's actually getting new data, like not our testing data, another new data, we see that its generation error has is increased a lot. Now why does this happen? Because unknowingly we have kind of trained our learning rate to best fit for our testing set. Now this is a problem. So to solve this, one idea is of cross validation. That is basically we divide our uh, training data and testing data. We have our training data and testing data. We keep our testing data as untouched. We only work with our training data. What we do here, we divide our training data into further different parts, and we these parts are called folds basically, and we train on one and then use one for testing, and then finally when we have done with our all models we just use a testing set one. But this can cause a problem that your training data might be just too less if you just keep dividing it like that. So what we do actually is we still divide our training data into a few folds. Suppose we divide into 5 folds or 4 folds or anything. We take suppose we are dividing our training set. We're only talking about our training set, not the entire set. The testing set has been completely separate. This was our 70% training data. Suppose we divide it into 4 parts. What will we do? These are just randomly selected, just like training and testing splitting, which is we take random 70% and random 30%. Suppose we equally divide it into 4 parts, 1/4 of this 70%, each of this randomly picked. Now, what we will do at a time for 100, we have 100 of these models. We'll do what? We'll train them on any 3 parts and do the testing on any one part. Like we train on this and we test on this. Then we suppose we train on this, we test on this, and so on. Now, this will allow us to get a good optimal value for the learning rate. And when we have finally we are deduced a good value, we finally train one last model with that particular learning rate, and then we check a generalization at just one time on the testing data set. We'll now move to the coding portion for linear regression. For this, I'll be using the California housing dataset. I've taken it from Kaggle.com. You can check it out. Kaggle is a very good website for datasets if you want any. So first of all, we are importing necessary libraries, NumPy for numerical computations, Pandas for data manipulation, Matplotlib for visualization, and Seaborn is a library built on top of Matplotlib. This allows for some advanced visualizations. So we'll first of all we'll read our dataset into our data frame. Now, if you we can do df.h to check our dataset. You can see it has longitude, latitude, housing median age, total rooms, total bedrooms, population, households, median income, median house value, and ocean proximity. As you can see, all of these are numerical attributes except this. This is a categorical feature. And we'll be predicting the median house value. This will be our target variable, and the rest of these will be our input features. Now we can run some basic commands for data exploration. For example, if we do df.shape, we see that there are 10 columns here, which we can also see from here that there are 10 columns. And we can see that about 20,640 data tuples here. That is the number of data points that we have. If we do df.info, we can get some information about all these fields. You can see that out of this many data points, almost all of them are not null except for total bedrooms. So total bedroom contains some null values. Apart from it, everything else contains not null values. And you can see that all of these are float 64. That means all of these are numerical, and this is an object. So this is actually a categorical feature which we can also observe from here. Now if you do df.describe, you're going to get some so this basically tells us some statistics about all of our numerical features, such as count. Count basically tells us the number of data points that have not null values for that particular feature, which we're also getting from .info. We also have the mean of each numerical attribute. We also have the standard deviation, the minimum for all those values, the maximum of all those values. The 50%, this is basically the 50th percentile. This is basically the median of that particular feature. The 25th percentile is basically if you arrange the data in sorted order, what will come after 25% of the data. 75 percentile is basically if you arrange the data in sorted order, what comes at this after 75% of the data. You can see the statistics about all of these different attributes. Now, if we check our missing values, we can do df.isNull.sum, and this will tell us that none of them have null values except total bedrooms, which has 207 null values, which we all can also observe from above. Now, how do we handle the missing values? We fill them up with some other value like the mean or the median for that feature. So here we'll use the median. So if you see what was the median for uh, this thing, total bedrooms, the median was actually this 50%, that was 435. We could have also imputed it with the mean, by with this process called imputing. We can also fill it with the mean, which was 537. However, the mean can be skewed by some outliers in a data set. The median is more robust, so we are preferring that. If it were a categorical value, we would have done with the mode, because then the median would have made much sense. Now, for our model to work properly, we need to convert everything into numerical features. So whatever categorical feature we have, we must convert them into numerical as well. So we'll use something called one-hot encoding. Now, what does one-hot encoding do? It basically creates a new column for each of your different category in the categorical feature. So for example, in ocean proximity, if we have suppose 5 different features, it will create, as if we have 5 distinct classes in that, it will create 5 different columns for each of those classes. Now we do drop first equal to true. That basically it drops the first column, so it only keeps the 4. Why? Because if all 4 of them are false, like if the second, third, fourth, and fifth are false, it is obviously implied that the first one would have been true. So this just removes some redundancy from the data set. Now if you do this and run it, you can see that we have converted our ocean proximity into the different categories. The ocean proximity, inland, island, near bay, and near ocean. You can see there are only 4 of them here, while there were 5 of them originally. We have dropped the first one. Now we can check the target distribution. Our target was the median house value. You can see it is the curve is like this. It is slightly skewed towards the right, and there is a big bump here. Now we check the correlation matrix. So you can see this is our target value, the median house value. You can see it is mostly correlated with the median income. So the median income is very important to predict the median house value. We can also see that these features are also highly correlated with each other. The total rooms with the number of household, the population, and total bedrooms. The total bedrooms with the households and population. The total population with households and itself. That's obvious. So this can introduce multi-collinearity in our dataset. So what we want to do, we want to do some feature engineering to combine these features into one or two feature to remove this collinearity and redundancy from our dataset. So first of all, we can check this one, like the median income to our median house value. We can check this plot. You can see it's not really, it is kind of linear, but again, it's very skewed from there. You can see this diagram, it's something like this curve. Now we create some new features, bedrooms per room, which is the total bedrooms upon the total rooms. We create rooms per household, which is basically total rooms upon households. We create population per household, which is population upon the total number of households. Now this basically captures all of the information of these columns, so we can now drop these as to remove redundancy. Now if we check our data set, we get something like this. We have our categorical columns here, and these are our new columns that we just created, and we have dropped the old ones. Now, if we now draw our correlation heat map, we can see that all of that collinearity is gone. The only thing we have here is with the target output, that is median house value is highly correlated with median income, which is to be expected. Now we split our data set into two parts, X and Y, our input features and our target. Now we take our data set and we do a 70-30 or 80-20 split into a training data set and a testing data set. The training data set will be used to train our model, and then we'll test it on our testing data set. So for this, we'll use a library called scikit-learn. What is scikit-learn? Scikit-learn is a high-level library that is used for machine learning tasks. It is a very good library and we'll be using it for all of our models. We do not need to implement the model from scratch. Scikit-learn provides all of them with all of the different metrics and all that. One thing it provides is train test split. This is a function that splits your data set randomly in the given ratio into your training and testing data set. The test size specifies how big your testing data set will be. I have given here as zero point 0.2. So it's a 80-20 split. 80% of my data is going to be part of my training data, and 20% of my data is going to be part of my testing data set. This random state is just used for reproducibility of results. You don't worry about that. Now feature scaling. Why do we need feature scaling? Because all of our numerical values, suppose one thing would be in kg, one could be in meters. Even here you can see that the magnitude ranges are quite different. For longitude, it's like between -1 to 4 and -114. It's in the negatives. The latitude is like between 41 and 32. The median age is like between 1 and 52. The house value is like between 15,000 to 50,000, 5 lakh. So you can see there is a lot of difference between the magnitude. So we want to scale them to a similar level so that they're comparable. If we don't do that, the higher magnitude features will dominate the lower magnitude ones, and we won't be able to learn from those. So if we see here, from SQL under preprocessing, we can import standard scaler. This standard scaler basically scales our data set according to the standard normal distribution, that is with 0 mean and 1 standard deviation. So we instantiate it as scalar, as standard scalar. Now our training data would be, we are calling two methods on our training data, fit and transform. We're calling fit transform. This is basically two methods combined in convolution, dot fit and dot transform. However, since it's a separate function, it's more optimized. Now what, and on our testing data, we're only calling dot transform. Now what does fit do and what does transform do? So fit basically learns from our data. Here we want our z-score normalization. So we want to compute the z-score, x minus mu by sigma. So dot fit will learn from our training data what is the value of sigma and mu for each of our features. and then dot transform will apply that mu1 use that mu1 sigma to apply the transformation to our actual data set, which is what's happening here. On a testing data set, we are not applying fit. We're only doing transform. Why? Because we don't want to learn from a testing data set. That is separately only for our generalization. So we only apply transformation so that we can scale that as well. Now to train our linear regression model, we first import it. So from sklearn.linear model, we import linear regression. We instantiate it. So model equal to linear regression. And then we fit it. Model.fit x train y train. So now what is dot fit does? This is basically training our model. The model is learning the values for the parameters w0, w1, w2 up to wn by the process of gradient descent. And again, I said like fit is used for learning the values. So it's learning the values of those parameters. Now, if we were to do some predictions based on our model, we can use the dot predict method on our testing data set finally. Now we can check our errors. So from sklearn metrics, we can import mean squared error and root mean squared error. And we can see that these are our values. We can see our root mean squared error is about 71,000. That means on average, our predictions are off by $70,000 or 7,000 bucks. This is not really good given our dataset range, but since our model is linear, I guess this is what we can do. Here you can see the house value was between 15,000 and 5 lakhs. The mean was like 2 lakhs. The median was like 1.8 lakhs. So RMSE of 70K is not that good, but it's decent enough, I guess. Uh, Another metric is R2 score. We didn't really talk about it, but R2 score basically tells us how much variance our model has captured. So for example, here we can do from sklearn.metrics import R2 score, and then we can compute the R2 score between our test y test and y pred, and it comes out to be around 62%. This basically tells us that our model has captured about 62% of the variance in our dataset. That is, has captured about 62% of the underlying pattern of our dataset. Again, it's not that good, but it's decent enough. Now, if actually we plot our predicted and actual data sets, so basically the closer to the diagonal, the better would it be. Basically, for one, if the actual value was one, we wanted to predict one. If it was two, we wanted to predict two. So the closer it follows for y equal to s, the better it is. Here you can see it is slightly curved, so it's decent but not that good. And the residual analysis is basically the actual minus the predicted value. You can see the graph looks like this. So this was about linear regression. Now we'll move to logistic regression. So let's talk about logistic regression now. Now this is also a supervised learning algorithm, but it is used for classification. Now you might be wondering why is it called regression when it is a classification algorithm. So historically, regression term was used to just refer to a relationship between two variables. It was not necessarily for continuous values, and the names come from there. And another thing is that this does not really output discrete values. It actually outputs a continuous value between 0 to 1. We interpret those values as probabilities, and we assign a threshold that is basically zero point 0.5. If the generated value is greater than zero point 0.5, we say that the data belongs to class 1. Otherwise, say the data belongs to class 0. So this is basically a binary classification model. That is, there will only be two classes, a class 0 and class 1, negative class, positive class. Example could be a spam filter, like the mail is going to be either a spam or not a spam. Again, stuff like that. Now at its core, logistic regression is also a linear model. What does that mean? Just like linear regression, we are going to compute this value. Like if we have the input features as x1, x2 up to xn, we're going to find w0 plus w1 x1 plus w2 x2 up till w1 xn. This is what we're going to compute. But this is not going to be our final answer, because obviously like this has can go anywhere between the real numbers. This does not necessarily need to be between 0 to 1. So we are going to apply a special function to it. So to get in linear regression, this was our predicted value, but here we are assigning it as z. It's not a predicted value. Our predicted value y hat is actually sigma of z. Now what is sigma? Sigma is a very special function. It is called a sigmoid function. We'll talk about it now. But first, logistic regression being a linear model, what does that imply? So this basically implies that whatever data set you have, that has to be linearly separable for it to work perfectly. For example, let us consider this data set. Let's suppose the red points belong to one class and the blue points belong to another class. You can see that a straight line can separate these two classes very well. So this data set is an example of a linearly separable data set. A logistic regression tries to find this separation line. Now, you might wonder what if the data is not linearly separable? Well, logistic regression still will try to find the line of best fit. It won't be perfect, but you can still find something. Now, moving towards the sigmoid function. So, sigmoid is a very special function. It is given by sigma of z as 1 upon 1 plus e to the minus z. This is graph. This is basically a mapping from all real numbers. It squishes it down to the open interval 0 to 1. This basically converts our predicted values and converts them into probabilities. Now, if the probability is greater than zero point 0.5, that is greater than equal to 50%, we say that the object belongs to class 1, otherwise say it belongs to class 0. We also say class 1 is the positive class and class 0 is a negative class. You can call them class A, class B, anything you want. So what does our predicted value y hat actually signifies? So our predicted value y hat is basically the probability that the real value was 1 given our input features x. That is, it is the probability that our data set, given our data set, that our current point belongs to class 1. That's why if the probability is very low, that means it belongs to class 0. Now, if you talk about why do we use the sigmoid function, as in what is so special about it. So one thing is that it converts all real numbers into probabilities between 0 and 1. That is one thing. Another thing is that this function is smooth in its entirety of domain. You can see it is a very continuous curve. Also, it is differentiable everywhere. We generally try to find functions that are mathematically convenient for us because for gradient descent, we need to compute their derivatives. So sigmoid being easy, the gradient being easy to find. Like if you find the derivative of sigmoid, it's just sigmoid times 1 minus sigmoid. So even its derivative is very easy to compute, which we require for gradient descent. Also, we generally try to find functions that are continuous everywhere in its domain and also once or at least once or twice differentiable in its entirety of domain. That's why sigmoid here is very useful. Now, if we talk about how does the training process works for logistic regression, again, we fit the parameter values for these parameters, W0, W1, W2, W1. So it is exactly like linear regression. We have some loss function and we try to minimize the loss to get the values of these parameters. Then the only difference is that we take sigmoid of this and then do the output, but the training process is quite similar. What's different is our loss function. In linear regression, we use something called the mean squared error. But here the mean square error will not make much sense because you only have two discrete outputs, 0 and 1 as our final outputs. So the error will always be either 1 or 0. So it won't really be a good metric to consider. So the cost function that we used for binary classification is the log loss or binary cross entropy. It is basically given as minus 1 by n times. Now this y is the true predicted value and this y hat is the predicted value by our model. This 1 minus y is a probability that it would belong to class 0 and this 1 minus y hat is our model's predicted value of it being belonging to class 0. This is a true value of it being to class 1. It's been a true our predicted probability of it belonging to class 1. This is called the binary cross entropy. We're taking by dividing by n to standardize with the number of data points, and this minus is just to make things positive. So this is our loss function. We try to minimize it through gradient descent and update our values of our parameters. Suppose we have a very simple model like again z equal to w naught plus w1x. Suppose so these will be our trainable parameters. Obviously we're going to have y hat as sigma of z and then we'll apply gradient descent to optimize find the values of w naught and w1. Again w naught will be assigned the value of w naught minus our learning rate times. This time we're going to take our loss function as j, this thing, log loss or binary cross entropy, and we're going to differentiate it with respect to w naught. And for w1 is going to be the same thing, just the gradient will be with respect to w1. Similarly, if you have other parameters, the gradient will be with respect to those. Also, computing these gradients are very simple because if you assume this equation for z, and then y hat is going to be a sigma of z. If you try to compute del z by del w naught, you're just gonna get y hat minus y, and with w1 is gonna get y hat minus y times x. So again, these are very simple to compute, so that will save our computation time during the training process. Now for classification task, another important thing to consider is that your data sets must be balanced. If you have an unbalanced data set, that is, suppose you have, if you have a binary classification problem, you have two classes, class 0 and class 1. Suppose 90% of your training data is of class 0. The model can just learn to just say everything is class 0 and get an accuracy of 90%. So to avoid these kind of things, we must always train our model on a balanced data set. So if a data set is not balanced, how can you make it balanced? So there are two techniques, two forms of techniques, undersampling and oversampling. What are both of these used for? Suppose you have a minority class and a majority class, and by the way, this also generalizes to multi-class classifications. You should have almost equal number of data points from each class. So for your minority classes, what you can do, you can oversample them. What does that mean? That means you can just duplicate those data points. One solution is that, for example, if you have 10 data points from your minority class and 40 data points from your majority class, you can try and duplicate your minority data points 4 times. So now you have 40 data points of each. Then you can train a model. However, this does pose a problem of overfitting. So you must not practice it too heavily. Like this poses this threat. So what are the other techniques that we can use? Another thing that we can do is undersampling. Now, what does undersampling mean? Now, this does not cause overfitting. Now, you can guess what it does. If you have 10 data points of your minority class and 40 data points of your majority class, you only take 10 data points from majority class randomly and just train on those 20 data points. But now this causes a threat of underfitting because it is possible that your data set is not enough. You do not have enough data to fit your model on. So there are problems with both of these techniques. There are some other more standard ways to do that. Like one better way to do oversampling is there's a technique called SMOT, although you don't need to get into it right now. Uh, it is synthetic modification of training data. It actually stands for synthetic minority oversampling techniques. So what you do here, suppose you have two data points of your one class, and suppose you have other data points of other class that don't matter, and you can have other data points of this class also. What you do, you take your minority class points. For example, here red is in minority. You always not in two minority, but you can see that. What you'll do, you'll take any 2 points. Suppose I'm taking this point and this point. What we'll do, we'll extrapolate them, we'll connect them, and we'll make a new point between the two. So now this is a better way to oversample, and this reduces the risk of overfitting. However, if your data is noisy, this is also an issue because you will just introducing more noise into your data set. Anyways, keep in mind that you must make sure that your data set is balanced before you start training your model on it. Now let's talk about some evaluation metrics for classification algorithms. Now, as I previously said, the mean square error does not make much sense here. So what does make sense here? Like we're classifying our data points as class 0 or class 1 as a negative class or a positive class A or class B, email as spam or not spam, and etc. So one metric could be how many data points did the model classify correctly. So before that, we'll talk about one thing called the confusion matrix. So suppose as the row we have the actual classes and as the columns we have the predicted classes by our model. So suppose if the actual class is 0 and the predicted class is 0, all those data points that were actually 0 and were predicted 0 are called the true negatives. Why? Because they belong to a negative class and they were correct, so that's true. Now if your actual data point were from class 1 and their predicted is class 1, so they belong to the positive class as we are designating one as the positive class. That those will be called true positive. Now, if in actuality your data point was from class 0 and your model predicted it to be a class 1, so your model thought it was of positive class, but that's obviously false. So that's why it's a false positive. Now, if in actual the data point belonged to class 1 and your model predicted to be of class 0, then your model predicted that it would be in the negative class, but that's wrong. So it is a false negative. So this matrix basically tells us out of all of the samples that we are feeding it, how many are true negatives, how many are true positives, how many are false positives, and how many are false negatives. Now we can use these four to derive some metrics. The first of them being accuracy. Now accuracy is the most obvious things that comes to our mind. It is basically the number of data points that are predicted correctly. That is all of the true negatives and all of the true positives upon the total number of data points, which is the sum of all of these. Another thing, uh, two other things that are there are precision and recall. Now, what is precision and what is recall? But before that, what was the problem with accuracy? The problem with accuracy was that if your training dataset or testing dataset was skewed, the accuracy would be useless. Suppose you are doing a binary classification and you are training it with a sample of data. Suppose 90% of your training data was actually from class 0 and only 10% was from class 1. Then a model can just try to cheat its way and just give suppose class 0 every time, and it would be right 90% of the time by default of the value of a data set. So here accuracy is deceiving. So that's why we have some other metrics, namely precision and recall. So what is precision? Precision is the number of true positives upon the all of the positives predicted by the model. This is basically how precise your model is. That is, of all the positives that the model predicted, how many were actually positive. Another similar thing is recall. Now, recall is how well the model was trained. That is, how well its memory was. Basically, out of all of the data points that were actually positive in the original data set, how many could the model remember to be positive? This is what we call recall. So, if you see, precision is just true positive upon this row, the predicted positive row, and recall is a true positive upon the actually positive. So this row. Now there is something called the precision recall trade-off. Generally, as the precision increases, the recall decreases, and as the recall increases, the precision decreases. This is a relationship, so we cannot just take one value as high and be content with it. So we kind of combine these metrics, both of them into one, and call it the F1 score. Now this is basically the both the precision and recall combined. This is you might be saying like what is this? This, if you observe carefully, this is just the harmonic mean of precision and recall. Now what's good about the harmonic mean? It is that it will only be higher when both of these values are higher. So it kind of gives us the best of both worlds. Okay, so that was all about logistic regression. Now we'll take a look at its code. So now coming to the code for logistic regression, here I will be using the PIMA Indian diabetes dataset. This is a dataset about how many people have diabetes in India. We'll import this required libraries, NumPy, Pandas, Matplotlib, and Seaborn. I've already uploaded this dataset, so we'll just read it. And this is our data frame. You can see that we have pregnancies, glucose, blood pressure, skin thickness, insulin, BMI, diabetes pedigree function, age, and outcome. Now this outcome is a predicted class. You can see the values are 1 and 0. This 0 is basically the patient does not have diabetes, and 1 is basically the patient has diabetes. This is our target variable, and all the remaining are our input features. Now if we do some basic data exploration, we can see that the shape of our dataset is 768 cross 9. That is, it has 9 columns, which we can see from here. One of them is the target column, and the rest are our input columns. And there are 768 data points in our data set. If we do some info, we can see that, okay, here we can see that all of our data types are numeric in nature, so there are no categorical columns here. And we can say that out of the 768, all of them are non-null. That is, there are no null values in our data set, at least from this. When we do df.describe, we get some statistics about our numerical attributes. Now here we can see a few things. We have the minimum value of, observe the minimum value of a few of these columns. The minimum value of pregnancy is 0, glucose is 0, blood pressure is 0, skin thickness is 0, insulin is 0, and BMI is 0. Now these values are not biologically possible. So what are these? These are basically invalid values. So these are basically, we can treat them as null values, and we have to remove them from our dataset, or we can not remove, we can impute them with the mean or the median of that particular column. So first of all, we'll check how many of those columns are there. So we can see that 5 in the glucose, 35 in the blood pressure, skin thickness is 227, insulin is 374, and BMI is 11. So even though initially it looked like it had no null values, but these are essentially null values, invalid values or null values. You can say that. Now we'll handle those values by imputing them with the median. So we'll do that. We'll call the fillna method. First of all, we replaced 0 with np.nan, not a number, to denote that it was a null value. Then we filled all the null values with the median of that particular column. So now if we check our target distribution, you can see that our data set is not very balanced. Like the number of zeros looks noticeably higher than the number of ones. That is, the number of people not having diabetes is significantly higher than the number of people that have diabetes. Now, this can cause some problems in data set, but we'll talk about it later. Let's move further. So if we talk about the feature distribution of our data set, you can see the different plots of our data set. This is a plot of pregnancies, glucose. You can see the distributions. This is a bit left skewed. This is quite centered. This is also looks quite centered. This is very left skewed. This is also left skewed. This is slightly left skewed. This is slightly left skewed. And again, our outcome, this kind of plot is not really necessary because we only have two values, 0 and 1. It's basically a count plot. Now, if we check the correlation between our different features, we can see that our with our outcome, glucose is the most correlated one. So glucose is quite important to tell if a patient has diabetes or not. None of the other input features seem too highly correlated, so we are fine in that. Now to check for our outliers, we can draw some box plots. Now what are box plots? They're basically used for identifying outliers. So what do we do here? This line is basically the 50th percentile. This is basically our median. Now this is basically we tell from the 25th percentile to 75th percentile how many data points are there. Anything that is, and this reason called the interquartile region, IQR, anything that is before like the 25th percentile minus 1.5 IQR or after the 75th percentile plus 1.5 IQR, that is considered as outlier. For example, in this diagram, we can see that in BMI we have these many outliers, in age we have these many outliers, which you can also observe from the graph of BMI and age. This was quite skewed, this was quite skewed, and glucose has does not seem to have any outliers. So we can see from here that glucose was quite centered in its distribution. It was not skewed. Now going further, we'll split our features and target into X and Y. X is our input features and Y is our output. We'll split our dataset as 80-20 again using sklearn train test split. We again kept the test size as 20%. Now we are again doing feature scaling. We imported standard scaler and we're calling fit transform only on X train. We're calling only transform on X test. Why? Because we don't want to learn from the testing data set. We only want to make it learn from the training data set. Now what this is doing again? The fit is learning the value of mu and sigma, that is the mean and standard deviation of each numerical feature. And then the transform is applying using that mu and sigma to compute a z score, x minus mu by sigma for each of those values, and then replacing that with the actual data so that all of the magnitudes are normalized so that no higher magnitude column dominates some lower magnitude column. Now we import our logistic regression model. So from sklearn.linear model, logistic regression also linear model. It is linear by nature. We import logistic regression. We instantiate our model, and then we call fit on it. Now what is fit? Fit basically allows it to learn the values of all those parameters w0, w1, w2 up till wn. Now if you see here, if I just run these, I guess I should not run this. Yeah. So if I just run this, uh, yeah, so now my model has been trained. Now if we see the predictions, we can call the model or predict on it. And what is predict probab? This is basically, you know how logistic regression outputs probabilities. It outputs a number between 0 to 1. and we interpret that number as class 0 or class 1. If the probability was greater than 50%, we call it class 1. If the probability was less than 50%, we call it class 0. So you can see that from here. If we just check the first 5 samples, you can see here the probability was 53%. So it was class. Here the probability was 5%, so it was class 0. Here it is 87%, so it's class 1, 78% class 1, 12% class 0, 55% class 0. So this is just proof of that. Now we'll talk about the accuracy. So from SQL metrics, we can import accuracy score. We see the accuracy we're getting here is about 77%. Now we can also get a confusion matrix. This is this. Now this is class 0 and this is class 1. These are the rows are the actual and the columns are the predictor values. We can visualize it from using a using a heat map. This looks better. So we can see that 85 data points were true negatives, 34 were true positives, 23 were false negatives, and 12 were false positives. Now we can also compute the precision, recall, and F1 score. So from sklearn.metrics, we can import our classification report, and here we can get all of those for both of the classes actually. We did not really talk about this support. So this support is the actual number of data points from each class. So in our testing dataset from class 0, we had 97 data points. And from class 1, we had 57 data points. So this support shows that. Now, what is this macro average and weighted average, what you're wondering? So the macro average is simply the average of these two values. So for the precision, the macro average is just this plus this by 2. For recall is just this plus this by 2. For F1 score is just this plus this by 2. And then the support is just, since we're considering all of the data points, is just the sum of these two. The weighted average, the macro average just did an average blindly, but the weighted average weights is according to number of data points. So it's actually the support into this plus 57, 97 into this plus 57 into this upon 154, and this is 97 into this plus 57 into this upon 154, and so on. So that is how we get these metrics. So this was all about logistic regression. One thing I also wanted to tell you was, let's go back here. We can see that our data set is disbalanced. Now, I told you previously that this can cause problems with our model, but the model can just learn to classify more things as class 0 to get a better accuracy. How can we fix this? So I said a couple of ideas about like smooth and oversampling and undersampling. So another idea similar to oversampling is of weighted, assigning weights to the minority class, where whenever a minority class comes, we give it more weight. This is kind of similar to like duplicating the points, but we're not actually duplicating them. We're just getting a similar effect by assigning them weights. So we can also do that. Here I can train another model. I'll just call it model 1. This is another logistic regression. Here we can see that we can take a number of different parameters. We're talking about we are interested in this class weight parameter. So we'll do class weight and we'll keep it as balanced. Now what this does is, now I'll fit my new model, this one, model 1. I'll fit it on my X train and Y train. So now this is a new model that I've trained which has taken this imbalance into account. So this should in theory give us better accuracy. Let's check it out. I'll call this as model 1.predict and model 1.predict. I'll just call it ypred1 and yprop1. Let me just copy this and I'll not change this. I'll just create some new, and then I can just print this. So there are some changes here. We are interested in these metrics. So we'll try to print this for our model one. I call it accuracy one. Let's call it y test and y pred one, I believe. Yeah, and accuracy score is not defined. I guess this was, yeah. So now we're seeing that our accuracy has increased from 77% to 81%. We can also see the confusion matrix, like we don't need this much. We can just look at this. Should we wipe red one? You can see that this has changed a bit. Let's plot this as well for our new model. You can see previously we had more of class 0, now we have less of class 0 in the true negatives. And we'll also get its classification report. And yeah, so you can see that the precision has increased, and as the precision increases, the recall has decreased. That is the precision recall trade-off. But you can see that the F1 score has slightly increased. Uh, for for the majority class, slightly increase, but we have interest in the minority class. So one was a minority class. We can see that the F1 score for the one has increased significantly. Also, the true positives for the one class has also increased, and the accuracy of the model has always obviously increased when we are giving weighted samples. So this was all about logistic regression, and this was all from our side for this session on machine learning and these study jams. So hope you guys had fun with it. We'll be giving out induction tasks shortly, so look forward to that.